Swayam Prabha. Digital India. Educated India.
Welcome to the module 3 of the lecture series on design of transmission elements. This third module is related to introduction about bevel gears, its nomenclature, and at the last design methodology for design of bevel gears. So first of all, we will study about the introduction about the bevel gear, thereafter bevel gear geometry and terminologies, and bevel gear force analysis, bending stress analysis, contact stress analysis, fatigue bending strength, fatigue contact strength, and the factor of safety. Now if we compare the bevel gear with the two gears which we studied in our previous modules, the spur gear and the helical gear, then both of those gears were made on a cylindrical blank. Cylindrical blank, you see here, this is a figure of a spur gear and this is made on a cylindrical. Now if you compare the bevel gear, then bevel gear is made on a conical part. So bevel gears are cut on mating cones rather than the mating cylinders of spur or helical gears. So this will be a cone, this will be a cone of a pinion, this will be cone of a gear. Now the spur gear and helical gears were used to transmit power between two parallel shafts like this. Two parallel shafts, one of the gear was like this and the mating gear was like this. The shafts were parallel, but in the case of bevel gear, the shaft will be not parallel, but it will be intersecting. So the axes are non-parallel and intersect at the apices of the mating cones. So the cones are mating at a point and that is called the apices of the mating cones. Now the angle between their axes can be any value and is commonly it is 90 degree. That means the axis between the two shafts, this is the axis of the one shaft and the axis of another shaft is this one. So they are not parallel and they are intersecting, and the angle between the two shafts may be any. This may be 90 degree, this may be more than 90 degree, more than, or it may be less than 90 degree depending on the requirement. This is showing, this figure is showing a bevel pinion and bevel gear which are cut on a cylindrical cone. This is showing the pitch cone of the two gears. This is the one pitch. This is the pitch of the pitch cone of the gear. This is the pitch cone of a pinion. You may see here, these are the mating cones and apices. This is the apices. The pinion is this one, the gear is this, and the axes are intersecting at this one. This is the angle between the axes, and this is the cone. This one, and this is the cone for the gear. The mating apices. This is another view of the pinion and the gear. Now this is the gearbox where the bevel gear is used. This is an example of differential which is used in an automobile, and you may see the propeller shaft shown in green color, this green color, which is getting power from the drive line, and at the end you may see a bevel gear which is rotating this crown wheel. We will study what is the meaning of this crown wheel. And this is the small gear, it is again a bevel gear, bevel gear, bevel gear, bevel gear. Why these bevel gears are used? Because we want to change the direction of rotation. They are the wheels, rear wheels on these two sides. This is the axle, outer half shaft, and this is the inner half shaft, and the power is to be given along this direction, which is 90° to the axis of the propeller shaft. So with help of bevel gears it is achieved, and some other purpose is also achieved, and that is the differential of the rotation of the rear wheels with the help of this bevel gear. Because when we go in the corner, then the inner wheel, this wheel of a vehicle, has to rotate with a small RPM with comparison to this one, because in a same time this wheel has to travel a smaller distance in comparison to the outer wheel. So in a same time different distance these two wheels has to travel. So the speed of this wheel should be smaller on the corner in comparison to this wheel, and that is achieved with help of this differential and with help of the bevel gears which are used here. The differential is shown again. There is the motor is given, the propeller shaft is getting power from this motor. This is the shaft axis, and the axis in which you want driven power is this one. So angle between the shafts is 90°, and which is achieved with help of the bevel gear sets. Now if the teeth are cut parallel to the cone axis, okay, now you see here the teeth are cut parallel to the cone axis. The cone axis is the okay, it's parallel to the cone axis. Then it is called the parallel bevel gear. You see, this is analogous to the spur gear. Now if teeth are cut at a spiral angle psi to the cone axis, they are spiral bevel gear, analogous to the helical gear. In the helical gear, we have seen that the teeth were inclined by an angle, helix angle psi. In the case of spur gear, you see here, in the case of spur gear, the teeth are parallel to the axis, but in the case of your helical gear, they are not parallel to the axis. If the similar case is there for the bevel gear, so see here, the teeth are not straight but they are curved. See, like this. It is more visible here also. It is curved like this. So this is called the this is the spiral bevel gear. There is a spiral bevel gear. Now, similar to the helical gear, these gears are recommended for higher speeds, recommended for lower noise level, because there will be again gradual engagement and disengagement. This figure again shows you a spiral bevel gear. So it is clearly visible that the teeth are curved like this. This is the top land of the teeth. Well, in the case of pinion also, you may see the way the teeth is curved. Now, contact between the teeth of straight or spiral bevel gear has the same attributes as their analogous cylindrical counterparts, the spur gear and helical gear. So, in a case of straight bevel gear, it will be analogous to the your spur gear, and for the case of spiral bevel gear, it will be analogous to the helical gear. Therefore, spiral bevel gears run quieter and smoother than straight bevels, and spirals can be smaller in diameter for the same load capacity. Spirals are recommended for speeds up to 40 meter per second. Higher speeds require precision finished gears. As with spur and helical gears, a maximum reduction of 10:1 is recommended for any one bevel or spiral gear set. A 5:1 limit is recommended when used as a speed increaser. If a bevel gear is used to increase the speed, that means the driving gear will be the gear and the driven gear will be the pinion. Then the maximum speed increase shall be 5:1. The torque on the pinion is used as a rating parameter. So, the torque which acts on the pinion or the power which you transmit with the help of pinion will be the rating parameter, and so the pitch line velocity which you will determine, that will be based on the pinion diameter and the RPM of the pinion. So, it will be pi d of the pinion and RPM of the pinion divided by 60. If d is in mm, then it will be in mm per second. The most common pressure angle for bevels or spiral is phi is equal to 20 degree. We have seen what is the pressure angle. Pressure angle is the angle between the pitch line, which is tangent to the pitch circles, and the line of action. The similar definition is there. So, spirals most often have a 35-degree spiral angle psi. Bevel gears in general are not interchangeable. They are made and replaced as matched sets of pinion and gear. So, if in a set of pinion and gear, one of the gear is damaged, then that particular gear is not replaceable. You have to replace both pinion and gear. When intersecting shafts are connected by gears, the pitch cones, analogous to the pitch cylinder of spur and helical gears, are tangent along an element, with their apexes at the intersection of the shafts, as in figure, where two bevel gears are in mesh. See this figure, in which the pinion of the bevel gear is shown here and the gear is shown here, and they are sectioned, and so the gear tooth, which is visible for the gear, is shown here. Now, as these teeth are cut along a cone like this, and so the thickness of the gear tooth will be different at this end and at this end. Okay, this is called the small end and this is called the big end. And along the cone, the width of the teeth will be B. So this is one of the tooth. Another, which is mixed with the tooth of pinion, is shown here. And another tooth of the pinion, which is visible in section, is this one. Okay. So the cone, which is the line which is passing through the pitch points, is this is the pitch cone of the pinion, and this one is the pitch cone for the gear. Okay, so this is your pitch cone, gear, pitch cone. Similarly, the pinion pitch cone will be this one. Well, so the size and shape of the teeth are defined at the large end, because the size is varying when you are moving from this end to this end. So the size is defined from the big end, where they intersect with the back cone. Now, if this is extended, see, if this is extended and this side of the teeth is again extended, then the cone which you are getting is called the back cone. Okay, this is the gear back cone, and the gear pitch diameter will be measured from the big end, and so the gear pitch diameter will be this one, from this to this. Well, this is DG. Similarly, from the big end, when you will see the distance between these pitch circles, this will be your pitch diameter of the pinion, DP. Well, now if a circle is drawn with the this dp as a diameter and center where the back cone is intersecting. Now, if a circle is drawn with radius given by with the radius given by this R, B, P and center where the lines drawn from the back intersects. So, this is called actually the back cone, this one. This is a back cone. So, from the apex of the back cone, taking that as a center and radius equal to this one, this distance. Let me make this in this is the radius. This one. This is your RBP. RBP. That means radius of the back cone of the pinion. So, with that radius, if a circle is drawn, then that circle is called the pitch circle radius of the virtual spur gear. And for the pinion. Similarly, the back cone for the gear is this one. This is the back cone of the gear. And the apex of the back cone is this one. Let us say it O dash. Then if we draw a circle with center of circle equal to O dash and radius given by this distance. This to this one. This distance, then that circle is so this will be the pitch circle radius. The circle will be the pitch circle and this radius will be the pitch circle radius of the virtual spur gear. This pitch circle radius is called the developed back cone radius. Now, in the this bevel gear mesh, different nomenclatures are there and those nomenclatures we will study in the next slide. Here a single gear bevel gear is shown in section and different nomenclatures are shown. This is your pitch line, this and this, which forms the pitch cone. Well, and so the diameter corresponding to this from the big end is the outside pitch diameter or simply pitch diameter of the gear. Why it is said outside? Because when you will see from the small end, then this diameter from the small end will be the inside pitch diameter, but as we know that bevel gears are defined from the big end, and so this will be called the pitch diameter of the gear. Pitch diameter of the gear. Now, when we will see the from the big end, the gear will just look like a spur gear, like this. Well, it will have this outer diameter, it will have pitch diameter, it will have base circle, it will have dedendum circle. Okay, all circles will be there, very much similar to the spur gear and the helical gear. And so the height of the gear tooth at the big end from the pitch circle to the addendum circle, this outside circle is called the addendum, and that is shown here. This is the addendum. Similarly, the bottom part is dedendum. Is the dedendum. Addendum is called HA and the dedendum is called HF. And along the pitch, the length of the gear tooth is called the face width B. Well, now when this apex of the pitch cone is joined with the top land, this is the top land, and joined with the bottom land, then you will get these two lines, this and this. Now, so this is the pitch cone line, this is the pitch cone line. The angle between these two is called the 2 times the pitch angle, and the angle between this pitch line and the axis of the rotation is called the pitch angle. So this angle is the pitch angle, which is represented by gamma, pitch angle gamma. Now, the angle made by axis and the root, the root cone is called the root angle, and the angle made by the face cone with the axis is called the face angle, which is shown here. Now, from the apex, this length is called, when you will extend it, it is called the cone distance. Now, the angle between the pitch cone and face cone, well, there are 3 cones. The first is the pitch cone, well, and you have teeth like this here and at this end, big end and small end. Now, when this is joined, this is called this is the face cone, okay, and when this is extended and this is also extended, then the cone which you are getting, this one is the root cone, okay, this is the root cone. The outer one is the face cone and the middle one is the pitch cone. Well, and similarly you will have the root angle, the pitch angle and the face angle, and some additional angles are there. The angle between the phase cone and pitch cone, the addendum part is called the addendum angle. Similarly, the angle between the phase cone and the pitch cone is called the addendum angle. This is the, no, it is dedendum angle. Addendum angle is this one. Okay. And outside diameter, this is the inside diameter, and along the pitch cone, the radius which you are getting is the pitch radius r. Now let us define the terms which we just discussed. The pitch cone is an imaginary cone surface of which contains the pitch lines of all teeth in bevel gear. Cone center O. The apex of the pitch cones is called the cone center. Apex of the, this means this one. This is called the cone center. Then cone distance L. The cone distance is the length of the pitch cone element. That means the pitch cone, this is the pitch cone. So length of the pitch cone element is called the cone distance, capital L. It is not the length of the face cone or the length of the root cone. It is length of the pitch cone. Then pitch angle gamma, the angle that the pitch line makes with the axis of the gear, is called the pitch angle. So the meaning is, let this is your pitch cone, this is axis of rotation. So the angle between this is called the pitch cone, pitch angle gamma. Addendum angle alpha, the angle between this pitch cone and the face cone, this is alpha. This is face cone, this is pitch cone, the angle between this is alpha. Then dedendum angle delta. Dedendum angle delta is, you have this pitch cone and here is the center line or the axis of rotation. Okay. So the angle between this pitch cone and root cone is called the dedendum. So it is the angle subtended by the dedendum at the cone center. So dedendum will be somewhere here, bottom is the dedendum, and so the angle subtended by dedendum on the apex center will be the dedendum angle. Then face angle, gamma plus alpha is called the face angle. Gamma is the pitch angle and alpha is the addendum angle. So this completes angle, this one is called the face angle. Then root angle, pitch angle minus dedendum angle is called the root angle. Then back cone, the back cone is an imaginary cone and its elements are perpendicular to the elements of the pitch cone. Back cone radius RB, it is the length of the back cone element. We see the pitch cones is this one, this is pitch cone of the pinion, and pitch cone of the gear is this one. These two are intersecting at the apex of the pitch cones and intersection of shaft angle. This is the axis of the gear shaft, this is axis of the pinion shaft. So when gear is viewed from this end, a tooth looks like a spur gear, but size will be bigger in comparison to when it is looked from the small end. This is called the small end, this is called the big end. This will be the small end, this will be the big end. So here if you will see the gear tooth, it will look like this, smaller, but at this end it is bigger. Similar is here. The gear tooth is bigger at this end, and at this end you may see from this side this is smaller. The thickness is smaller, and that is visible in this figure. This is the small end of the gear. Tooth thickness is less in comparison to the big end. Big end. This is the big end, and it is visible that you see the gear tooth is bigger, and the top land is not rectangular, it is tapered. See the top land. In the case of spur gear, the top land was rectangular, just like this, and so throughout the width the teeth was or gear tooth were similar. See, this type of thing was there. Like that. But in this case, you see the teeth thickness, shape are entirely different, and the top land is tapered. This is called the big end, tooth thickness more in comparison to small end, and along the pitch line, if we see the thickness, so if at the small end thickness is T dash, and at big end the thickness is T, then T is greater than T dash, and therefore the bevel gear is defined from its big end, because which thickness we have to take. So either we have to select this small end or the big end. So the big end defines the bevel gear. This is the sectional view in which the different part of the bevel gear is shown. OEIO is the pitch cone. OEIO is the pitch cone. Okay? You may join it like this. So OEIO is the pitch cone, and BCFG B is representing a gear tooth. Similarly, at this end, this and this is representing a gear tooth. BG is the small end and CF is the big end, and EI is the pitch diameter. E to I is the pitch diameter, this one. So I is the pitch diameter which is shown here. Then OCJO is the face cone. OCJO, C and J is joined, then OCJO is the face cone, and when this CF is extended and this JI is extended, follow the yellow line, then it is intersecting at O dash. Then the distance IO dash or EO dash is called the back cone radius, and the back cone is O dash IEO dash. Okay, and this back cone is perpendicular to the pitch cone element OEIO. OEIO is the pitch cone, and EIO dash E is the back cone. Now let's find what the values are for a gear in a mess, the values of the cone distance, values of the pitch angle for the pinion, pitch angle for the gear, for a particular case where the angle between shafts is 90 degree. So this diagram is showing a case in which the angle between axis of rotation of the pinion and angle of axis of rotation of the gear is 90 degree. You see this is 90 degree. Now for this 90 degree configuration, we have this CB is the pitch diameter, isn't it? CB is the pitch diameter, and so O, which is the apex where the pitch cone of the gear and pinion are intersecting, this O, B is the cone distance. Okay. So this OB or OC, both are same. OB or OC, you may write here, OB is equal to OC, and that is the cone distance. And to determine this cone distance, let us take the triangle OAB, or you may say OAC also. This triangle you may also take. Now in this triangle, the AB, in the triangle OAB, we have AB is equal to, AB is half of the pitch diameter of the gear, and the pitch diameter of the gear is DG, that is CB. Okay, CB is the pitch diameter of the gear and that is represented by DG. So AB is half of the pitch diameter of the gear, and that will be DG divided by 2. Now what is OA? OA will be the half of the pitch diameter of the pinion, because if this point is taken as capital D, then DB is the pitch diameter of the pinion. Represented by DP. Okay, it is shown here, DP. Well, so this OA is half of the DP, this one, this distance. So OA is DP divided by 2. So OC or OB or OC is given by OA square plus AB square. Well, that means under root of the OB is equal to under root of the DP under root of the DP divided by 2 square plus DG divided by 2 square, and that is shown here. Now we can find expressions for pitch angle. Now pitch angle for the gear is angle AOB. Angle AOB is the pitch angle of the gear, and that is shown here. Gamma G. pitch angle of the gear gamma g. So this gamma g can be determined in terms of pitch diameter and the gear diameter, again taking the triangle OAB. So tan of the gamma g is equal to AB divided by OA. AB is DG divided by 2 and OA is DP divided by 2, and so tan gamma g will be DG divided by DP. So gamma g is tan inverse DG divided by DP, or if by taking help of a module this DG is changed to number of teeth, then this will become equal to ZG, number of teeth on the gear, divided by number of teeth on the pinion. Similarly, by taking triangle OB and this E, triangle OBE, we can find pitch angle for the pinion, that is gamma P. This gamma P, which is this angle. Gamma P is tan inverse pitch diameter of the pinion divided by pitch diameter of the gear, and tan inverse number of teeth on the pinion divided by number of teeth on the gear. In some cases, bevel gears are classified on the basis of pitch angle. Three types of bevel gears that are based on pitch angle are as follows. When the pitch angle is less than 90 degree, pitch angle means the angle between axis of rotation and the pitch line. This is the pitch line. Well, and gear tooth will be like this. So this is your pitch angle gamma. So when the pitch angle is less than 90 degree, okay, it is called the external bevel gear. When the pitch angle is equal to 90 degree, that means this angle is 90 degree, well, then it is called the crown bevel gear. In that case, what will happen? This will become like this. This is the axis of rotation and this angle is 90 degree, gamma is 90 degree, and so gear tooth will be like this. It is just analogous to the rack in the case of spur gear. When the pitch angle is more than 90 degree, it is called internal bevel gear. More than 90 degree means if this is the axis of rotation of the shaft, then the angle is this one, this is the gamma, and that happens for the case of internal bevel gear. Now there are certain specific categories of bevel gears. They are as follows. The meter gears, when the two identical bevel gears are mounted on shafts which are intersecting at right angle, they are called meter gear. That means the pinion and gear both is same, number of teeth are same, the pitch diameter is same, and so the gear ratio will be 1. Okay, Zg divided by Zp will equal to 1. This is equal to MP, it is equal to 1 for the case of meter gear. The pitch angles of pinion and gear of meter gears are same and each is equal to 45 degree. That means this is the shaft angle and both are same, and so this pitch angle will be 45 degree for the case of gear, and for the pinion it will also be 45 degree. The gamma P and gamma G both are 45 degree. They rotate at same speed. Now crown gear. In a pair of bevel gears, when one of the gears has a pitch angle of 90 degree, then that gear is called crown gear. You see this one. We have seen the crown gear where the pitch angle is 90 degree. So for the case of 90 degree, this is the pitch angle gamma, and this is axis of rotation, and so gear tooth will be just like this and this is shown here, this one, and it is mixed with the regular pinion, okay, and so the angle between the shafts is more than 90 degree. Such bevel gears are mounted on shafts which are intersecting an angle that is more than 90 degree. The crown gear is equivalent to rack in spur gearing. The pitch cone of the crown gear becomes plane. Now, hypoid gears, when two spiral bevel gears are mounted on shafts which are non-parallel and non-intersecting, they are called hypoid bevel gear. Now, till now we have studied the case of bevel gears in which the axes of the shafts were intersecting each other. Now, the axes are non-parallel and non-intersecting. Hypoid gears are based upon pitch surfaces which are hyperboloids of revolution. When two hyperboloids are rotated together, the resultant motion is a combination of rolling and sliding. These gears are mainly used in automobile differential, which is shown here. These gears allow the drive shaft to be placed well below the center line of the rear axle and thereby lower the center of gravity of the vehicle. This is very much visible here. This is the crown gear. The axis of the crown gear is perpendicular to the screen, and the pinion which is meshed is having axis shown here. So, the axes are non-parallel and non-intersecting. Axis of the pinion is this one, and the axis of the crown gear is perpendicular to the screen. But these two are offset with each other. The meaning is, if this is the axis of the propeller shaft, and this is the axis of the gear of a differential, then you may keep the axis of the propeller down, and so the center of gravity of the vehicle will become down and it will become stable. Here you see the shown here, this is the crown gear, and the axis is this one, and the axis of the pinion is this one. They are non-parallel and non-intersecting. Now see how with the change in place of the pinion, the gear changes. Then if it is along the axis, then spiral bevel gear, then it comes to spheroid or helicon gears, and later on if again the same thing is shown. If the axes are intersecting, then spiral gear. Now if some offset is there, you are moving further, the shape is changing, it becomes spheroid, and later on if it is perpendicular it becomes worm gear. Spur gear is considered in a plane perpendicular to the tooth at the large end. That means we have seen the back cone. Now if this line is extended, a back cone with the radius equal to back cone radius. Now with this back cone radius, back cone lines are intersecting this center, we draw a pitch circle and make a gear, then this is called the virtual spur gear. of a bevel gear. This is shown here. This is extended from this pitch point. This is the pitch point. Here it is extended. So this one is the back cone. The lines are intersecting here. This will become the center of the virtual spur gear, and the radius will be that. This red color is the back cone, and this O dash B is the back cone radius. So with this radius, a gear is made. So the module is called the pitch circle diameter divided by number of teeth. So in a triangle ABC, this is called the A, B, and this one is C. This is the triangle. Okay. Angle ABC is the gamma. ABC is gamma. AB is D divided by 2. BC is equal to RB. BC is RB, and AB is the half of the pitch circle diameter of the gear, because if this one is taken as D, this point is taken as D, then DB is the pitch circle diameter of the gear, and AB is half of the pitch circle diameter, and so AB is D divided by 2. And angle ABC is gamma. Why? Because this angle is gamma, this angle is gamma, pitch angle, this is 90 degree, here it your O, angle AO and B is gamma, and so this angle is 90 minus gamma, so this angle is gamma. So angle ABC is gamma, AB is D divided by 2, and BC is RB. So cos of the gamma can be determined from the triangle ABC, and that will be AB divided by BC. AB is D divided by 2, and BC is the pitch cone radius RB. So RB is given by D divided by 2 cos of the gamma. Well, and from the module we get M is equal to D divided by Z. So this we can substitute here. D is equal to M multiplied by Z. So if RB is the pitch circle radius of this imaginary spur gear, and ZV is the number of teeth on this gear, that means it is extended like this, and we have gear tooths. This is the pitch circle with radius equal to RB. Okay. And number of teeth on virtual spur gear is ZV. The gear is called formative gear or the virtual gear, and the number of teeth ZV on this gear is called the virtual or the formative number of teeth, and that is given by 2 RB divided by M. The working depth of the teeth is usually 2 times module, the same as for standard spur and helical gears, but the bevel pinion is designated with the larger addendum, that means 0.7 of the working depth. This avoids interference and results in stronger pinion teeth. It also increases the contact ratio. The gear addendum varies from 1 module for the gear ratio of 1 to 0.54 module for ratios of 6.8 and greater. The gear ratio can be determined from the number of teeth, the pitch diameters or the pitch cone angles, as tan gamma p is equal to dp divided by dg, and that is zp divided by zg, and that is rpm of the gear divided by rpm of the pinion, and that is also given by cot gamma g. accepted practice usually imposes two limits on the face width of the gear tooth. This one was the gear tooth, this is the pitch cone. So this length is the face width B. So the limit imposed is the B should be less than or equal to 10 times module, or B should be less than or equal to L, where L is the cone length divided by 3. Now this is all about the general introduction about the bevel gear and different nomenclatures which are used in the bevel gear, or the different type of bevel gears which are used based on the shaft angle, based on the pitch angle and other applications. Now in our next class, based on this introduction, we will study the forces which acts when bevel gear mesh transmits power from driving gear to the driven gear. Thereafter, with help of these forces, we will find the transmitted load, or the load which is transferred from driving gear to the driven gear, or the useful component. And with this, we will do the stress analysis. We will find what type of stresses will act on the gear tooth when the power is transmitted. And later on, with the knowledge of strength of the material, we will find the factor of safety, or we will find whether the gear is having strength enough for transmitting power which is required. Thank you.